Hello, welcome back to our monthly Fireside Chat. For those of you that are new to the MOOC on Coursera, or maybe new to the Fireside Chat, this is an event that we do every month with a guest speaker, and we try to explore topics of interest that we think will get you excited, and maybe talk about some applications of experimental design methods that you might find interesting. For those of you that are on Coursera, we post all the Fireside Chat recordings to the courses, and you can find them in the Resources tab of your course. And there are a lot of them. We probably we're into the 40s now in terms of the number of Fireside Chats. So I encourage you to take a look at what's out there, and I'm sure you'll find quite a few interesting things. Quick reminder about audience etiquette. Please continue to keep your microphones muted, your cameras off during the session, so that we don't get any extraneous noise or other disturbances that would be a distraction. My guest today is Mr. John Davies, Jay, from the U.S. Army DEVCOM Chemical Biological Center at Aberdeen Proving Grounds. He's a research physicist with that organization, and he specializes in applied statistics and design of experiments with over 30 years experience in both federal service and private industry. His expertise in process optimization has led to multimillion-dollar savings, including a simple $5 O-ring solution that saves $400,000 per month. Since 2021, he has collaborated with over 120 researchers on more than 60 projects applying experimental design methods to such diverse fields as DNA synthesis, biomanufacturing, chemical agent decontamination, and additive manufacturing. His problem-first approach and DOE methods have accelerated research efficiency, enabling unexpected scientific discoveries while reducing experimental samples by up to 95%. And he continues to mentor researchers in DOE applications in a wide range of fields. I'm really pleased that we're having Jay with us today, and he is actually live in the studio. So here he is, and we're going to let him take over the Fireside Chat at this point.
Okay, thank you, Dr. Montgomery. Really excited to be here. I thank you. I thank ASU for inviting me to appear on this Fireside Chat. This is something I'm very passionate about. I enjoy it a lot, and I enjoy sharing my experiences. I am a researcher at the Army Combat Capabilities Development Command. We're at Aberdeen Proving Grounds, specifically with the Chemical and Biological Center, and we come up with decontamination solutions for chemical warfare agents, biological agents. We also do detection, and we also do protection. I have just some acknowledgments here. Some of the people that have mentored me early on in DOE have helped me along. I want to express my gratitude. And of course, remember the researchers that I work with at the Chemical Biological Center, they're the PIs on the project. Those are the subject matter experts. I'm just bringing the experimental design and the statistic capabilities, and I'm also mentioning our funding agents here. Up front, I just want to say that all the views and opinions that I express here, things that I talk about, they're the opinions of the authors, namely me, and they don't necessarily reflect any position or policy of the U.S. Army, the Department of Defense, or the federal government. I may mention DOE softwares by name. That's just my personal preference. Those are the things that I use. DOE, this stuff works really great. It has wide applicability. It greatly improves your experimental efficiency. And in my 20 or so years in industry and with the Chemical Biological Center in federal service and research, we found that it works for a wide variety of fields of study. It's low cost, low risk. And in this talk, I'm not going to get under the hood much about how the mathematics and the statistics works. I found that many of the researchers that I worked with, they already had a pretty sound understanding of statistics, but a lot of times they'd never really been exposed to DOE, or they never looked at DOE as an applied technique, something that they could actually use. So I like to concentrate on the wow factor. Look what DOE can do for you, because if I can get them to run one experimental design they're usually so impressed that they're hooked. So this will be, hopefully, I'll express my passion that I get from running these designs. And I think you'll see some, I have 4 case studies I'm going to talk about, and I think you'll see we've had some impressive results. And my life story, this is my path. How did I end up in DOE? In high school, I really gravitated toward physics. I liked physics, and I also liked fixing things, cars, mechanical things, electrical things, hands-on repair, studying things, taking them apart. I guess that kind of led me to a path of studying physics in college. Before I even graduated, I started working with a solar cell startup company that was run by a professor in our university, and ended up making the first stages of my career. Spent 15 years with them. And I would say in 1995, in the middle of that, was my first exposure to DOE. I happened to take a miscellaneous Introduction to DOE course in 1995. We used Dr. Montgomery's great text. I had some statistical background. I was fascinated with what can be done with this DOE. But remember, this was a while back, and the course was purely academic. We generated ANOVA analyses by hand. We generated designs by hand. We never really got to the sections about optimal design. And the course didn't have a laboratory. They didn't give us any software. And we never really were shown how to practice, how to put these things in practice. So that seed kind of stayed in my head, but unfortunately never really used DOE at the solar cell company.
Sadly, that's still the way a lot of people teach design and experiments.
Yeah, exactly. Yeah.
And it just kills me that that they're not taking advantage of.
In your text, there were several examples, but I don't even know if we skipped them or didn't really focus on them.
Yeah.
It was purely from an academic. So here I am sitting in a solar cell environment.
Yeah.
We're collecting all kinds of data. I could have had a field day if I would have had someone at the company who encouraged me, hey, let's try to put this in practice, or if I had the handy software that we have now. So yeah.
I was very fortunate in that the first course I took in statistics was at Virginia Tech, and it was taught by Ray Myers, one of the great heroes of the world of experimental design. And then I took an undergraduate elective course in experimental design from him, and it was enormously practical.
Yeah.
Again, we didn't have computer software, but you really, Ray was able to show you the power and the utility of the method, because he was a chemical engineer by training, an undergraduate, and he had lots of consulting experience, and that all came to play, and I was hooked.
Yeah, I was never exposed to somebody that actually had the experience doing DOE. So, and we're very busy in this startup company, so it kind of sat dormant. Then I went to a ceramic composites manufacturing company, and this was a milestone in my career. In 2007, I took a Six Sigma Green Belt course, and Linda Bartowski, the instructor, early on made the comment, "This stuff will change your career." And she was referring to structured problem solving, having project charters, data analysis, data-driven decisions, and including DOE. I didn't pay much attention to that at the time. However, they did hand out a software package, and at the ceramic composites company, I started applying these techniques of structured problem solving, defining the problem before trying to work on it, and I'll talk about a couple case studies from that episode, from that period later. Then finally, 2009, I end up at the Chemical Biological Center, and this is where I actually started using applied structured problem solving and DOE. Around 2011, we really started getting into them, and in the last 3 years, the number of DOEs has just exploded. So the bottom lines up front, things I'm going to be talking about, mentioned it a couple times already, defining a problem before trying to solve it is essential. And I know in the Coursera, Dr. Montgomery gives, I think it's 7 steps. The first one is concise problem definition. So many times people just gloss right over that, and they want to go to the last step, which is verifying solutions, conclusions, and recommendations. But there's a lot of utility in getting the first step right.
I'm sorry to interrupt you again, but I'm glad that you're mentioning this problem-solving process. I've been thinking about modifying it a little bit to have a step 0.
Yeah.
Form the team.
Exactly.
Yeah.
You
Get the right people on the team before you even start figuring out how to get a problem definition. Because if you don't have the right people on the team, you may end up spinning your wheels. For a long time.
What I've found, we all know who the subject matter experts are, but there's some of them that are unrecognized. In manufacturing environment, I found the people that touch the product on the floor, they are an untapped resource. And one of my examples later will show that the solution actually came from someone on the floor, which you wouldn't think necessarily in terms of their training, but they touch the product. They
operating personnel are key, and the other key that I have discovered is never let the person who is the expert on the problem be solely responsible for the experimental design.
Exactly.
Because they will design an experiment that is too narrow.
Yes.
That is intended to actually prove what they think is the answer.
Yeah, and you don't know what you don't know.
And you can't. You gotta figure out a way to deal with that, because I like the way you don't know what you don't know.
Yeah.
And unfortunately, the quote expert, they think they know the answer.
Yeah.
Yeah, we don't need to do this because I already know the answer, and that often leads to catastrophic results. But I'm glad you're mentioning this, because this is
Well, that's front and center.
This is really key.
2 of my case studies will speak directly to this.
This is really key.
With huge results. And one thing I want to say, in a real world applications, the practical sense, for people out there that are like me, that maybe have an intellectual understanding, an academic understanding of DOE, but have never, where the rubber meets the road, have never tried it, try it. It works. You won't believe how well it works. And I can say that from experience. Soft side issues versus hard side issues. So in promoting DOE, especially in the beginning, I found that if I talked about the hard side issues, those are things like the statistics, the central limit theorem, just the mathematics under the hood. That didn't get me very far, because most researchers kind of already believe those techniques. They know them, but they just... So I concentrate on soft side issues, and this is working against the culture of one factor at a time testing. The traditional things are always done. That's the soft side issue. So I concentrate on that when I'm promoting DOE. And finally, George Box said, statistics without subject matter expertise is really useless. And I always, when I'm working with the researchers, I always say that the statistics is not here to replace your expertise. As a matter of fact, it's going to be a catalyst. As Box said, it can be a catalyst to discovery. We're going to, there's a synergy between subject matter expertise and the efficiency of these statistical methods. When you put the two together, really good things happen. And we have a short video that we've put together at our public relations people at the Chemical Biological Center have put together, and it gives you an overview of the kind of things that we work on, and we'll play that video now. When we do a laboratory experiment, or any experiment for that matter, what are we trying to do? Oh, it's usually estimate the influences of factors of interest, how they affect the response, And then we also usually want to determine, well, where do we put those factor settings to optimize that response? Those are the two common objectives that I see. And common difficulties that we can never get around: experimental noise. You run an experiment, you're never going to get exactly the same answer twice. Confounded data, if you're doing one factor at a time, sometimes your structure is such that you're not going to see interactions between factors. And if you are testing one factor at a time, it's going to be very efficient. And sometimes the workaround is, well, let's just try a full factorial, every combination, do everything in replicate, and that runs into problems because it really blows up very fast when you get more than 3 or 4 factors. You know, this is how I was taught to do experimentation. 5th grade chemistry class. This is a 1952 text, my first book of science experiments. And I found this a couple years ago, actually, in a bookstore, but I found it interesting. When you go to the first page, an experiment is a test used in seeking the right answer to a question. That's one question. That sounds like one factor at a time. When you plan an experiment, you begin with one particular question that you want to answer. Again, one factor at a time. And when I think about my career through high school, through college, through my years with industry, I was basically still operating under this technique that's described in this youth book here. Change one factor at a time, see what you get, then change another factor. But with experimental design, we can move past that and test lots of factors at one time. And I'll just scan through a couple of the common traditional means of experimentation. Number one, the single factor study. If you only have one factor, I guess, yeah, one factor at a time works. But in a real world context, at least in our context that I've been in, you know, we got 5, 10, 15, 25 factors if we can have our way. So the one factor t-test it's got its place, maybe when you're starting out, but in the real world situations, it's not very useful. Method number 2, this one is more common, and I saw a lot of this in industry and in research. When in doubt, just run the full factorial, and I'm showing 5 replicates here, which is probably a normal number. If you see 20 to 30 to 40% relative standard deviation, if that's your noise level, you might do 5 replicates. And you can see, when you get up to 4 factors, your study is already 400 and something samples. And I've seen those. I think I've occasionally seen 5 factors done in replicated full factorial, but after that, it's not doable. And just looking ahead, with DOE, we've run 11 factor studies, we've run 15, we've run a 35 factor study, and I'll tell you, we weren't doing 7 million or 71 million samples. We were doing maybe a couple hundred if we had 13 or 15 factors. So the brute force method doesn't work when you get more than 2 or 3 factors. We've mentioned already the OFAT, the change one factor at a time, intuition, trial and error. If you have subject matter expertise, you may get a pleasing result out of this, but it might not be very efficient, and you might miss some optimals or some things that you didn't know about because you don't know what you don't know. The drawbacks to all these methods that are not DOE is basically they're not efficient. They can miss true optimals. This is the good part. This is the stuff that I really like to talk about. I've got 4 case studies here. And the first one is from that solar cell manufacturing company. And we made solar cells. We made several different kinds. I'm showing a 6x6 cell here. It would go into a solar module as I'm showing here. Sometimes we put them in the modules. Sometimes we sold them loose. Things are going well. The company's growing. This is what our prime quality solar cell looked like, a rich royal blue appearance. But we started having this problem with what we called a picture frame defect. And if it's coming through on the video, you'll see it has a hazing ring around it. And we found that didn't affect the performance of the cell. We 100% checked for power. It didn't affect the longevity of the cell. It was purely a cosmetic. And you would think, well, it's going to go up on a roof. Who really cares? Not so. We would have to reduce the price about 40% and consider that a cosmetic defect to sell it. And when this defect was flaring up, it would cost us about $50,000 a month. And it would appear on about 5 to 30% of the product. And then it would go away. We would scramble to solve it, it would go away by itself. It may not be back for a couple months. We made extensive efforts to try to get to root cause. We took a very scientific approach and brought in a local university. They're studying with SMEs, EDACs. They're looking at the molecular level to try to find out what is causing that ring. Never did get to the root cause of it, but we determined that it is associated with this plasma edge isolation process step that was in the manufacturing line. And then this episode, the defect would come and go until one day it didn't go away. Weeks went on, a couple months go on, it's not going away. So now we're really serious. We have to find out what is happening in this edge isolation, this plasma isolation process that's causing this ring. If you skip the plasma edge isolation, the cells were perfect, they were beautiful, but they were all stone dead because they were shunted. So backing up one process step, before the edge isolation, this is the reason we needed to do the edge isolation. We're putting a diffusion layer down. We're going to make the junction on the solar cell, and it's a belt system. We spray a dopant, it goes through an IR furnace, and some of the dopant diffuses into the cell. I mean, very shallow, but that's our junction. But a side effect is some of that dopant wraps around the sides. That's the part we have to do in edge isolation. We have to clean that off, and that's what the plasma etch was doing. This is a conceptual of the plasma etch edge isolation process. First of all, you'll notice a vacuum chamber, and anyone that has time in manufacturing, when they hear vacuum chamber, it's ka-ching, it's going to cost you money. You have to maintain the pumps, you got to maintain the oil, you got to get rid of the oil. So in this process, we stack the cells up so only the edges are exposed in the chamber. We turn on an RF generator. We introduce a proprietary gas that creates a fluorine ion. This beautiful, very elegant purple plasma. We actually had an inspection window. You could see it. And it would isolate the edges of the cell. That's the way it worked. The root cause of the defect, the picture frame, is in this process. So when the defect didn't go away, it's all hands on deck. For weeks, we're having daily meetings in the main conference room. All the key players are in, trying to figure out how do we get this plasma etch process not to produce this picture frame defect. And here's the breakthrough moment. One day, someone finally asked the question, all we really need to do is isolate those edges. Isn't that right? And they said, well, if that's the case, we have a process just down the hall here where we're doing an abrasive blast on the surface, the fronts of the cells. Couldn't we reconfigure that to also do the sides? And, that seems to make sense. In theory, that could work. And the layout was through the wall here, about 150 feet away, was this abrasive blast station, and it's blasting the surfaces of the cells because we were reclaiming single crystal cells from the integrated circuit industry, so we had to rough up the surface before we went into our caustic etch. But it's only doing the surfaces. So someone had proposed this idea, and then we're thinking, well, maybe we're working on the wrong problem. Do we really have to come up with a scientific solution to this plasma etch when we've got this abrasive blast that may work just as well down the hall? So I was charged. I left that meeting. I went right to the machine. It took me about 15 minutes. I reconfigured it, manually put my arms in the glove box. About 15 minutes, blasted off the sides, put it in the production line within 2 hours. The next day they came out. They were beautiful. Picture frame defect completely gone. And we had these added benefits. When we looked at that process, we said, the capital equipment cost of the abrasive blast that we already have, it's much less than the capital cost for the plasma etch. It's 16 times higher throughput. It costs about $9,000 a month less to operate, and we only need, instead of having 3 operators per day, we only need about a half an operator because it's so fast. Within weeks, we put that into production. We also found as a bonus, the abrasive blast gave us 15% more power, so the plasma etch was never really doing a thorough isolation. Altogether, $160,000 a month savings for the solar company, coming from the idea of describing the problem, working on the right problem, and realizing we had the solution about 150 feet away from us. Case number 2, this is at the ceramic composites manufacturer. This is the $5 O-ring that saved $400,000 a month. So this company, we're manufacturing these ESAPI and SAPI plates that you see the warfighter inserting into their protective vest, their body armor. We made just the ceramic plate, and then another manufacturer would put the Kevlar and the epoxy on and put the whole package together. So this case study is going to, again, demonstrate the importance of defining a problem before getting involved in trying to come up with solutions. So here's the problem state. I'm working at this company in project engineering, but they invited me to come over and look at the process because they knew I had some experience of that at the solar cell company. So the initial problem statement was something to the effect of, we can't detect this defect until final inspection, and it's causing us $400,000 a month of scrap tiles. And That's real money because during this time the company had open orders. We could ship as many, we were only limited by our capacity and our yield. Anything we made, we shipped. So it was either throw it away or get paid for the product. So my team and I, we looked at the whole process. We looked at the serial numbers of the defective tiles. We traced it back to where they went through the process. We looked at dates, times, pieces of equipment. And the only correlation that jumped out at us was there was a particular machine in the process that had a process parameter I'm calling X here. And we found that when X was in the top half of its specification, this defect probability increased by about 20x. And this was we did a logistic regression fit to this. But we found when the control parameter was on its low end or its lower quarter, the probability of the defect went way down. So as all I did was read this description, these 3 sentences, just like I read them here to you. We were in a meeting with the R&D people, the management, the supervisors, engineers, and as soon as I said that, a R&D researcher stood up and said, "That's not just correlation, that's causation." We knew this in the R&D on the R&D bench 8 years ago, developing this product. We know that, and we know how to fix it. Go across the hall, get one of these O-rings, and put it in the machine here. So I did just that. I walked, it might have been 50 feet away, down the hall, got an O-ring, put it in the machine, and right away, parameter X became controllable. It wasn't as noisy. We could dial it down to its low end, within specification, but on the low end, and it stayed there. Pretty quickly, we converted all of the machines using these O-rings, and it was like a light switch. The defect virtually went away to the tune of about $400,000 a month savings. And the point here is we didn't have to come up with a scientific solution to figure out what the exact mechanism was causing this defect. Someone in the company already knew the workaround, the engineering level solution, and it was a $5 O-ring. And that's a huge savings to a 150 person company. So the next 2 case studies deal with DOE, and this is some of the definitions. I always get the question, well, what is DOE if they haven't heard about it? And I say, well, it's statistically rigorous. It's an objective way to experiment, to help you see through the noise. And Pat Whitcomb of the StatEase company that makes Design Expert, he says it's a systematic planned approach, rigorous techniques, maximizing experimental efficiency, and it can be applied to any process if you have measurable inputs, measurable outputs. And I found that the DOE is interchangeable with defining the problem before trying to solve it. It's very systematic. It fits in with that, and that's what DOE is about. And George Bach said it's just about determining what does what to what. Now I'm at the Chemical Biological Center. This is 2020. What you see in this picture is a spray-on decontamination slurry that works against chemical agents and bioagents. It can be sprayed on vehicles, on assets, tanks, what have you. And we first developed this a prototype formulation several years earlier, again using DOE for that one. Then we, with Army Research Lab, we improved it. It goes on as a paint. And in 2020, we were getting ready to move it on to commercialization. So we needed a final formulation, one formulation that is the best compromise for all circumstances. So we said, yeah, we need to do another mixture process DOE. So this is going to demonstrate how well mixture process DOE can work in a very complicated design space. Before I talk about the DOE, I want to show you, to get our samples, this is our panel testing process. So this DOE is going to use panel testing. And we have a 2-inch round panel. We condition it to a certain temperature, humidity. We put down the contaminant, and we're a surety laboratory, so we're working with live chemical warfare agents in microliter quantities, in environmental controls, in a fume hood, with all the proper procedures, but that adds a lot of cost, so samples are expensive to us. So we contaminate, then we cover it in a petri dish, and we wait for a predetermined amount of time, and during that time, the agent is diffusing, becoming absorbed into the panel. Depending if the panel is a permeable material, it happens a lot faster. After the aging, we do a flushing rinse that simulates a pre-rinse that they might do in the field. Then the decontaminant goes down. It's like the yellow slurry that we're showing here. It sits there for a certain amount of time. We do a rinse. We dry the panel. You can see some agent is retained in or on the panel. Goes into an extraction jar. We pull an aliquot. We go through a GC or LC mass spec. and we see how much agent was left, and we do a log difference reduction. How many log units did we reduce from the original contamination? So samples are expensive. You have to clean the lab up, you have to neutralize, you have to dispose of your materials. It's a slow and tedious process, so obviously DOE is critical here. This is the design space for this experiment. We knew we had a 5-component mixture. The zirconium hydroxide is the main active. There's 2 other actives and 2 extraction solvents, because if decon is a contact sport. If it's absorbed into the material, you have to have a solvent to pull it out to get it to the actives. So we know it's going to be 5 components. They're very wide ranges, which I'm not showing here. They could be like 0 to 50%. They're very wide. And the question is going to be, what's the single best formulation for all of these conditions? And the first condition is which agent we're working against. We have 5 chemical agents we have to go against and 1 bio agent. And if you look at the bottom, I'm going to multiply this out as if I was doing a full factorial, and we'll see how big this could get. Then we have 4 materials of interest. Some of these are permeable, some of them are not permeable. So now we're up to 24 combinations. And I can tell you that each agent material combination is very unique. These agents have different chemistries, they have different volatilities. The materials, some of them are hard, some of them are permeable, some non-permeable. Each of those is a very discrete scenario. But that's not all. The funding agency wants us to look at these continuous factors, the amount of contaminant you put down, look at the age time, how long it sets before you decontaminate, then look at the decon volume, how much decon did you put down, and how long did you leave it on there. And then, figure out what's the single best formulation that is the best compromise over all these conditions. And if you look at this full factorial at the bottom, I kind of said, well, maybe we would have used 5 formulations. We had 1 candidate formulation that kind of checked all the boxes. It was pretty good. And then maybe the SMEs would give us 4 others, because we can't test an infinite number of combinations. But even if we just picked 5, and we said, well, we have to do 5 replicates if we're not doing DOE, if these are standalone experiments, that's almost 50,000 samples. That's years of testing, several million dollars. So that just shows you that this problem could not be solved by brute force, or it was not going to be solved. And if we did that, what would we actually know? We would only know what happens with those 5 discrete formulations. We wouldn't have a predictive model. Of course, we did a mixture process DOE. So our proposal was we're going to use a special cubic on the mixture side, quadratic on the process side. We're going to use 3-way cross terms, and those are important because we have those 2 categorical levels, and we know that they are all very different. 489 terms in the model. We were going to do it in 10 days, less than 600 runs. We would include 35 exact replicates and 35 checkpoints. The checkpoints being the holdback validation points that we only use to validate the model but not to fit the model. And I'm showing what our predicted model would look like. Mixture terms plus cross terms plus the process model terms. Now, something strange happened at that point in 2020, which most people can probably guess what I'm alluding to. So before we could start this, COVID became prevalent. And they said, well, you guys can't have 10 days in the lab. We have to ration it out between all the programs. You might get 2 or 3. So we said, okay, that means 3, right? So we looked at our model and we said, well, hate to do it, but if we cut it down to 2-way cross terms and made it a KCV design, that would only be 184 runs, and we could do that in 3 days. Now, we thought we were going out on a limb with the 10-day design for a design space this complex. We're past the limb with this 3-day design, and we kind of caveated that. We said, we may have to actually go back and augment this thing. We don't know if we're going to get a good model from only 3 days. Well, so here's the design. Here's the comparison of designs. I noted with our contingency design, we're only looking at 7 samples for each of those 24 agent material combinations. And I'm thinking in my mind at this time, we are not going to be able to model all 24 of those agent material combinations only using 7 samples each with this formulation and with all those continuous factors. This is what the model looked like if anyone wants to see the equations. And these are the 3-way terms that we took out of the model to get it down to 3 days. To jump to the end of the story, it worked beautifully well. We were all very pleasantly surprised. This is your actual versus predicted plot. The black dots are the design points. The purple ones are the checkpoints that were not used to fit this model. They were only fit after the model was already reduced. And you can see we're fitting the checkpoints, the unknown points, just as well as the model is fitting its own design points. So this told us, yeah, this model looks like it is definitely not overfit, and we're predicting across 6 orders of magnitude. And is it a perfect predictor? No. It's within about 3/10 of an order of magnitude on average. But over 6 orders of magnitude, this was more than adequate to come up with the optimal formulation across, we did a multi-objective optimization across all the 24 agent material combinations. And we came up with the final formulation. We only used those 3 laboratory days. We never had to go back and augment it. And I'm proud to say the solution that the model came up with, which we went into the lab and verified, and it did work, it was as good as the candidate formulation for some of the agent material combinations, but on most of them, it was a half an order of magnitude to a full order of magnitude better in efficacy. And it was not a formulation that anyone thought going in, even the SMEs, where we would end up. But the experimental design was able to find it in that complex design space with only 3 days of testing.
If I were to encounter a problem like this today, I would probably look at using some kind of optimal design.
This was optimal.
Yeah, but I would have used like jump, for example, to create an optimal mixture process design.
Yeah, this was.
Okay, and that's
We're using Jump Pro, namely.
okay.
And we also use Design Expert kind of in parallel.
Yeah.
With this one was probably designed using Jump, but we kind of do them in parallel, and a lot of times we analyze them.
Well,
parallel.
both
Yeah.
packages have pretty good capability for doing
that's
mixture
exactly.
process experiments.
Yeah, this is a mixture process,
Yeah.
optimal design,
Yeah.
limited to 2-way crosses.
Yeah.
Yep.
The trick there is to specify the model that you want,
Yes.
and that's what saves you here is that you simplify the model.
Yeah, and we found in the literature, those KCV designs, that there were other groups that were getting good results. You would think you'd have to cross more than 3 terms, but they were getting acceptable results, crossing only 2, and we found that was the case, and that cut it down from a 10-day test to a 3-day test, which met our
That
requirement.
would greatly reduce the number of runs.
And we were anticipating that DOE is, you can augment it. So we thought, well, we may have to go back
Sure.
and do those other 300 runs, but when we were so far past the program requirements and what this formulation could do, that we moved on to it. We were done. We moved on to
and you
another
probably,
project.
even if you did some augmentation to improve the predictive performance, you wouldn't need to do all those runs. You could use the model that you've got to give you some ideas about where to do the extra runs.
I mean, and we use Jump and Design Expert. They have that augmentation feature, and you can augment against the original model, or you can put some higher order terms in, and it'll say, here's the ones you need.
Here's what you need.
And we've done that on some projects.
That works beautifully.
Yes.
A classic case where some sort of sequential experimentation in that mixture process space could really potentially be useful, but it turns out you didn't need to do that. I mean, these results are great.
We were very pleased that,
that
this worked.
These are
in
great
3
results.
days. So the final study that I'll talk about, the case study, this is still at the Chemical Biological Center in 2022, working with Dr. Garcia and Dr. Lux. They're the SMEs, they're the PIs in this. So they do synthetic biology. They work with cell-free systems, and they had a problem where they had 14 cell-free components that could be blended any way we wanted to blend them. And they also had automated an acoustic dosing machine that works in a 1400 sample well plate. It works at the nanoliter levels, so it can, whatever blends you tell it to make, it'll drop them into those 1400 wells, and it's all automated, hands off. So they had some pretty high automated throughput. They could do 1,000 samples a day of whatever blends you wanted. However, they were not using a structured DOE approach. So they looked at their 14 components, and they said, well, 3 to the 14th power, if we just tried to go high, medium, or low on all, we could have like 14 million or 4 million combinations for this formulation. Where do we start? And we know that there's nonlinear blending characteristics. Some of these 2-way, and there could be 3-way. So they had brought in an academic institution that had some expertise in AI ML. So they were thinking they were going to do an active learning routine where the AI would give us 5 blends. We would make them. We would report the results. The algorithm would iterate, and it would say, now do these 5. But when we talk to the experts, they're saying, well, this is a pretty complicated formulation. We may need to iterate 5 formulations. We may need to iterate a couple hundred times. And this system is very fast. I mean, we can get them an answer in 48 hours, but if you take 200 iterations times 48 hours, it still is going to be a long project.
Yeah.
About that time, we didn't get the funding for the collaborator. So now we don't have that option. So I'm involved in this project mostly because of functional data analysis. So if you look at the figure, you see those rainbow colored curves. I was working with this group saying, you're going to get a fluorescence response. JUMP has a capability, functional data analysis, where we can actually do a functional decomposition. It's like principal components, but for shapes. We can decompose those curves into scalar values and model the scalar values such that the DOE can actually predict the full curve rather than just trying to predict a landmark feature. So while my foot was in the door, so I said, 14 components, let's do a quadratic a mixture design. It's only about 150 samples, and I think that'll work for you guys. So they were maybe, they had let's see, kind of said, well, let's see how this is going to do, but we tried it. So this is an example where a very complicated design space, mixture process again, 14 components this time, and we ran 153 sample. This was a quadratic. It was eye-optimal DOE. This was built with a design expert and/or JUMP. We kind of build in parallel. This could have come from either one of them. 153 samples. They knocked it out in 48 hours. The curves that I'm showing, it identifies which came from the DOE samples. And you'll see we have some duds and we have some high performers. But that's a success. That's what the DOE is supposed to do. It's turning the knobs such that you're going to get a range of responses such that it can ferret out what are the active, it can fit the effects. Now, they were pretty happy when they saw some of those high curves from the DOE samples. They said, hey, that's pretty good. But I said, wait, that's not all. The model is predicting that we can get these curves up here if we go to these specific formulations. So I gave them a list of 30. They looked at that list and they said, you're telling us that some of the high performers are samples that only cost 1 cent per this was going down on like test strips or paper tickets. But they looked at some of those high performers and they said, that ticket would only cost 1 cent. A lot of what we see, they're $10 per ticket in some of those formulations. Some of those formulations could be $100 a ticket. Some of the cell-free components are very expensive. This particular design identified many optimals, and they grabbed that one that said 1 cent. We went in the lab, we made it, it performed the way that it should, and it was really quite an amazing discovery. And they have a publication that's been submitted and a couple others that are pending submission with this work. So, and we also found that with those 14 components, there were lots. There were about 12 pairs that had nonlinear synergies. So this was that's why I got the list of 30 optimals. Things, as you went down the pecking order, the formulation moved around quite a bit. This is a quote from John Tukey. The best thing about being a statistician is that you get to play in everyone's backyard.
One of my favorites.
You've played in a lot of backyards. So I've played in backyards around the Chemical Biological Center, a lot of them. Here's a graphic that goes up to 23. I haven't updated this for 24 yet. This shows 34 known DOE projects at the Chemical Biological Center that I've worked on, I've collaborated on with the SMEs. The whole we've done DNA synthesis, we've done the cell-free bio, we've done 3D printer filament optimization, we've done decontamination chambers, we've done things for the Navy with their countermeasure washdown. We've done robot optimization for a dispensing robot. It just gives a smoke grenade generation. It just gives you which is very interesting for me because it's a lot of different backyards. I've learned a lot from these SMEs. I'm just the DOE person, the statistics person. But you can see right around 22, about the time we did that cell-free bio, word really got out, and we did almost 30 DOEs in 23, and 24 is even a bigger number. 17 different programs, 11 different branches that shows the versatility. And once groups see the information that we're getting. And so what is the impact at the Biological Center? Here's a graphic that shows from 14 to 22. I picked 21 DOEs, and together those consumed about 2,700 samples. If we would have attacked that with full factorials or even half fraction factorials or non-design, intuition only, I'm estimating about 83,000 samples. That's a 97% reduction. And in terms of laboratory days, those studies consumed 87 total. We'd have been looking at about 1,800 laboratory days, those are expensive days. The DOEs consumed about mostly 1 laboratory day. A long DOE would be 4 laboratory days. But this just gives you an idea of the savings that, we're reducing sample sizes by over 90%. And I can show in many of these studies, even after that reduction, we're getting more information than we got out of the larger samples that were unstructured, that had confounding in them. So these sample sets are small, but they're very potent in their information content. This is a graphic just comparing full factorial studies versus DOE. The DOE is the number of samples for a number of factors. I think I built this for a response surface design. And these are actual experiments that we've done that fall into 13 factors, 17 factors. And this isn't updated. We've done formulation designs now with 35 factors. So now that we know we can work past 3 or 4, if you look at the brute force method, things blow up at about 3 or 4 factors. And the more factors you can have in the study, the more real-world application, operational operando, they're more relevant. They benefit the warfighter better because we have real-world factors in them. So just a summary of these 4 case studies: the solar cell picture frame, working on the right problem. The solution was staring us in the face 150 feet away, $160,000 a month savings. The body armor problem, again, the solution was already known. Once we determined what the proper problem statement was, and I'm showing here 960K savings. I didn't mention it, but there was 2 other situations where one of them involved an operator on the floor. We went through the data. We found that anything he was associated with, the yield was better. We eventually realized that there was one little step that he was doing that was in the control plan, but the other operators weren't doing it. We implemented that, and that was about another $200,000 to $300,000 savings. So out of that $960,000 a month savings, all those solutions were no cost and were created by just defining the problem. At the Chemical Biological Center, the decontamination slurry, we solved a very complicated design space, got a final formulation that's moving on to commercialization. It's a half an order of magnitude to an order of magnitude better than what we started with. And the cell-free biosensors, we've given that team a process where they can evaluate. They've done once we had that first study with 14, they said, hey, here's another 14 components. What can we get with those? Then we said, well, let's bring in 35 components. We've done several of those. So they have a process now. In 48 hours, they can come up with complex optimizations over systems with as many as 35, or who knows what the limit is. We're going to try 50 next. Here's just a little graphic wrapping things up. Cost and effort, DOE versus unstructured experimentation. Unstructured experimentation is always more effort, more cost. However, the DOE designs, while smaller, they're denser in information potency. You get more for your resources. So DOE is about collecting the right data. That's more important than having a huge volume of disjointed data. And DOE is giving us more useful information from less data. As strange as that sounds, that's what we're seeing. The key takeaways, just these were my bottom lines up front. I'd recommend anybody, don't gloss over that first step. Define your problem. Pull in the right people when you define that problem. The SMEs, the operators on the manufacturing production, they're SMEs too. They touch the product every day. You get a lot of opinions. Take the time to define your problem before going out and trying solutions. DOE works really well. I've showed you some examples. Those are just 2 from our center. I could show you 15 more that are nearly as impressive. Soft side issues are important when you're promoting DOE. I try not to get involved too much with the statistics under the hood when I'm trying to sell it, because if someone hasn't used it before, they may already have a statistical understanding, but I try to show them what this can do for them. And Box said statistics without the subject matter expertise is useless. He also said that statistics with subject matter expertise, that's the catalyst to discovery. And I've seen that over and over. Just some miscellaneous conclusions, things that we've talked to, and I thank everyone for listening to these stories, and I encourage you, try DOE. Dr. Tom Donnelly from Jump told me when I was trying to encourage me to do my first one, we were trying to make it perfect. We were waiting to get, he says, Jay, don't hold out for the perfect DOE. Do it right, build it properly, and run it. You're going to be so much better off than these large full factorials or intuition, and he was right. And once we saw that, we haven't looked back.
Jay, thank you. Your comments about stating the problem,
Yeah.
very important. I don't know if you're familiar with Charles Hicks.
I don't think so.
He was, for many years, a mathematics professor at Purdue. And he actually wrote a book on experimental design.
Okay.
A little skinny thing. Mainly it was how to do the ANOVAs for a group of different designs. It wasn't so much an experimental design book as it was a step-by-step. This is how you do the ANOVA manually for this type of design. And I know a number of people that took that course, and they said that he always made the following statement. He said, if you have 10 weeks to solve a problem, you should spend 8 weeks defining the problem.
Wow, I love that.
You should spend 1 week running the experiment and 1 week analyzing the data.
Yeah.
And he was trying to stress the importance of getting a proper statement of the problem with all of the, all the constraints and all of the variables and the pieces that you need to be able to do it. And I've tried to, get my students to understand that too, because I think it's a really important point.
Definitely.
And as I say, I would probably put a step 0 in there, which is form the team.
Yes.
Because if you don't have the right players on the team, you're not going to always have all the information that you need to be able to design a good experiment. And your idea about including the operating personnel,
Yeah.
really important. They know stuff that the engineers don't.
Exactly. Exactly.
And actually, so do the maintenance people.
Yes.
And sometimes it's even useful, if you can, is to get a customer, a user involved, because the customer or the user may have some perception about the response variable or other things that maybe impact decisions you make in designing the experiment. The other thing that I always tell my students to be careful about is understand the measurement system for the outcome. Not having a good measurement system and not making sure that it remains in calibration
Yes.
is key. If that goes wrong, you're in trouble. One of my colleagues here spent at ASU, Dan McCarville, you met him.
Yeah.
He spent many years working in this industry, and he was a quality manager for one of the Motorola fabs here. And they were having a terrible problem with a product that they were making for one of their automotive customers. It was some type of sensor that went in the engine controller. Dan got permission to shut the fab down for a week to run this really comprehensive experiment, which is going to identify the problem. Okay, and they finished the last runs in the experiment on like a Friday afternoon, and they had all of the parts. They had to go into the laboratory for some electronic tests and then some destructive testing. Dan talked to the lab manager and he said, okay, here are all the parts. And the guy said, don't worry. He said, I'm going to bring some guys in, over the weekend, and we'll get all this testing done,
Okay.
and we'll have the results on Monday. So Dan comes in on Monday and doesn't see any results. So he's walking around the halls looking for people, and he runs into one of the operations managers, not the lab guy. And he says, have you seen any of the lab people? He says, no, they're not in yet. And he said, well, do you know what did they do with all of those parts that were on that cart? And he said, oh, those parts. He said, we looked at the preliminary electrical test on that. It all looked pretty good, and we're so far behind on deliveries to Volvo that we put them on an airplane and sent them to Korea. They're being sliced and diced, and the chips are being sent to Volvo as we speak.
Oh man.
So the moral of that story is maintain control of the parts.
Custody.
Yeah, right.
Yeah.
And he and I still laugh about that because he says it was literally almost a disaster for their business because they were going to lose this customer if they didn't fix the problem. Eventually, they got it fixed.
Yeah, you can't be too careful when it comes to execution. When I put the DOEs together and working with the SMEs, I try to get the actual laboratory operators at least in the final meeting and go through. Here's the steps. Here's what this design table means, just to make sure everybody's on the same page. So it's going to get run the way that it's supposed to.
Yeah, particularly when all that testing has to be done offline, and
Yeah.
it's not being done literally as the samples are being collected. And so many times there are destructive tests and assays and things that have to be run that you can't do them in real time.
Yes. Yeah.
And maintaining, like I said, have somebody watching the hen house. It's
Yeah.
it's really important.
That's the way to put
Because
it.
I have seen a few cases, none quite as dramatic as that.
So they lost. They didn't get any results out of that
No,
study because it was
nothing.
It was
nothing.
a while.
It was all
After all that
gone.
effort.
It was all gone. Okay, well, I think we're done. And Jay, again, thank you for coming all the way out here to do this. We appreciate it. I always like to have live guests when we can, and hopefully you've had a good time with our Fireside Chat.
Excellent. Had a great visit. Enjoyed doing this, and
Great.
again, thanks for having me.
Thank you very much.